Hello, everybody. Welcome to section 2.2, graphs of functions. So we've already talked about sketching graphs in section 1.9, which we did by plotting a couple points, and then you kind of know the general shape of the graph based on like the general shape of the function, and then you can sort of connect the dots. But what about graphing like more general functions? So let's do an example where we graph a piecewise function. So what about graphing piecewise functions? So let's see an example of how to do this. So let's see, sketch, oops, a graph of, let's do f of x equals, let's do x squared plus 2 if x is greater than 0. And let's just have it be 3 if x is less than or equal to -1. So first off, we're going to do the exact same thing that we would do regularly. We're going to pick some points. So for my x, what I think I'm going to do is -2, -1, 0. And the 0 is going to be a special case I'll talk about in a minute, 1 and 2. So if x is -2, that is less than -1. So we're going to do this bottom case here. So it's just going to be 3. -1 is less than or equal to -1. They're equal, so that's still going to be 3. For 0, you'll notice the function isn't actually defined at 0. However, the x squared plus 2, the polynomial that the function is equal to everywhere above 0, is defined at 0. So while we can't really plug in 0 into this function to plot a point, we can look at where x squared plus 2 would be if it were 0. So you can't always pick the endpoint of a piecewise function like this if it's not defined at the point. But in this case, we can kind of sneakily sneak it in. And so this is kind of like plugging 0 into the quadratic. And so we get 2. And we'll see like how we deal with this when we go to graph it. And then for 1 definitely is greater than 0. So we use the quadratic. So we get 1 squared plus 2 equals 3. And then we get 2 squared plus 2 equals 6. So now if we go to graph, this is our x-axis, this is our y-axis. So let's see. We have -2, 3. So 3 here, -1, 3. It's also here. And then we'll do 2 goes to 6. So 1, 2, 1, 2, 3, 4, 5, 6 up here. Actually, let's do this in a different color so we can kind of see. Up here like this. And then we have 1, 3. That's 1, 1, 2, 3 is here. And we also have that like pseudo point 0, 2. So that would be kind of here. And because we have it's strictly greater than 0, it's defined. This isn't a point. So this is going to be an open circle right here. And this is why we wanted to kind of use the quadratic to graph it, because now we know like where that open circle endpoint should be. And so now we know that this thing is going to look kind of, the top one is going to kind of look like a parabola. So if I connect the dots, it's going to look kind of like this. Blink. And then the other one is the horizontal line. So it's just going to go like this. And this endpoint is filled in because it is less or equal to, right? Whereas if you have a strictly greater than or strictly less than, you get an open circle like we see here. Okay, cool. So graphing piecewise functions aren't actually that bad at all. So we're going to move on to a different kind of skill. So what if we start with a graph? How do we know that that graph represents a function? So our question is, which graphs represent functions? So which graphs represent functions? To answer this question, we're going to use the vertical line test. I'm sure some of you have heard about it before. So if we're writing it out in fancy language, the vertical line test says this: a curve in the coordinate plane is the graph of a function if and only if, so biconditional, if and only if no vertical line intersects the curve more than once. That is the vertical line test. But what does this actually mean in plain English? Let's see some examples. So example, determine if the following are graphs of functions. So let's see, the first one, let's do something that maybe looks like this. So just a little wavy boy. So if we pull out a vertical line, so if I use this ruler here and we kind of move it across bit by bit, we see that anywhere we move the ruler, the edge of the ruler only hits one spot on the green line at a time. So this is, yes, a function. It passes the vertical line test. All right, let's see another one. What if we had something like this? So this one wiggles in a different way. Now, if we use the vertical line test on it, we see that if we move it here, bam, we're hitting it in 3 different places. You're hitting it here, here, and here. So this one, no, this one fails the vertical line test because it hits it at more than one point. All right, maybe let's look at something maybe a little more complicated. So why don't we do maybe like a piecewise function. So let's draw something like, I don't know, open dot, and that line keeps going. Then underneath it, we're going to do, let's close dot here. Let's do this line, close dot, and then maybe, I don't know, something that wiggles off into the distance. Okay, so we want to know, does this graph represent a function? There's a lot going on, but let's just use our vertical line. Let's just pass it through. So we're doing good. We're doing good. And then, oh, we hit right here. Now the question is this a problem? And the answer is no, this is fine, because we're still only hitting it at one point, because the open dot does not count as a point that's graphed on the function. The closed dot does. And even though they line up, the open point does not influence this, because the graph doesn't actually reach that point for that top line. So we're good here. And we're good, we're good, we're good. And then even though there's no function here, that's totally fine. And then this one, of course, also passes. So this one is yes. This one passes the vertical line test. Let's do one more. Let's maybe look at maybe like a different case. So what if we do a line? Let's make it end. And then let's also put a point right here. So now if we use the vertical line test, we're good, and then we hit here, and then, oh no, we've hit this point right here, and we've hit this point right here on the line. And so even though there's a single point that screws it all up, this makes it still not a function. So this is no, fails the vertical line test. Okay, cool. So the vertical line test is a good thing to use if you have a picture of the graph already. So when we're looking at graphs of functions, we're going to want to kind of know like the basic sort of shapes that we're going to expect, so that if we look at a picture, we can kind of tell what sort of algebraic description of the function might look like. And if we look at an algebraic description, we might tell kind of the general shape of the graph. And this will come in useful, especially when we start looking at transformations of functions. So let's look at common, oops, can't spell as usual. Common functions and their graphs. So we talked a little bit about this in section 1.9, but now let's make a larger, more complete list. So linear functions, algebraically they look like this, pretty standard, where m is the slope and b is the y-intercept. So in slope-intercept form. And so we might expect them to look something like this, maybe like a horizontal line, or maybe some line like that. So those are both lines. Those are both linear functions. Note that vertical lines are not linear functions. They are lines, but they're not functions because they fail the vertical line test. And you can see that if you try to graph a vertical line and then apply the vertical line test, you'll run into an issue pretty quickly. Another general category is power functions. And all that means is that we have a function that is x to some power n, so 1 or 2 or 3. If it's 1, we actually do have a line. So usually when we talk about a power function, we're talking about its power being bigger than 1. So if we see some examples of this, we do f of x equals x squared, we're going to get our standard parabola that we've been seeing, like this. And then if we have maybe f of x to the third power, what we're going to see now is that instead of it going up in both directions, it's going to go up on the positive one and down on the negative side of the x-axis, like that. And then if we also look at f of x, and we do x to the fourth power, it's going to look kind of like the parabola up there, except it's going to be a little more squared off at the bottom here, like that. Just like that. And then similarly, if we look at f of x to the fifth power, this is going to look like to the third power case, except this time it's going to be more squared off, like that. So what you'll probably guess from looking at this is that, yes, if we have an even power, it's going to be pointing both up or both down, depending on the coefficient in front. And if it's an odd power, they're going to be, the two arrows going to be pointing in opposite directions on the graph. Cool. So those are power functions. Let's look at root functions. So if we do like f of x and the nth root of x, let's see, what do those look like? Well, kind of similar to the power functions, actually. We'll see a pattern as we play with the nth term. So this is square root, so there's a 2 there. Just note that. And so this graph looks like this, because it's only defined on 0 and positive numbers. And then if we also look at the graph of the cube root of x, we're going to see something interesting. This one is going to go this way, and then it's also going to go this way. Because if we have a odd root, it is then defined on all numbers. And then if we see f of x equals fourth root of x, then we're going to see something very similar to square root of x, except kind of more boxed out. So that one, this one appears rounder. The one on the bottom is a little more arched. And then if we look at f of x equals fifth root of x, you can probably guess by now what I'm going to draw. It's going to be something a little more boxed on this side and something a little more boxed on this side. Cool. So yeah, this kind of follows the same pattern as power functions in terms of what the root is. All right. Everyone's favorite, reciprocal functions. So reciprocal functions look like 1 over x to some power n. And so yes, again, let's look at what happens as we change n around a bit. So if we look at f of x equals 1 over x, we get a picture that kind of looks like this. We get this goes up to infinity, and then this curve right here. And then if we look at f of x equals 1 over x squared, we see that we get the same kind of picture, maybe a little boxier there. But this time, this one's going to be above the x-axis. And that's because the x squared makes things positive when we go ahead and graph them. Similarly, if we have f of x equals 1 over x cubed, again, the same pattern as the power functions. This one is going to be boxier, but still looks like this. And then you probably already know what I'm going to draw here for f of x equals 1 over x to the fourth, following the same kind of pattern we've seen already a bunch of times. It's going to look like 1 over x squared, except again, just a little boxier. So again, we see this alternating pattern. And the last one, of course, I'd be remiss if I didn't mention it, absolute value. We already know kind of what its graph looks like. It's just our standard V shape. All right, so this comprises a complete list of the kind of general basic function types that you're going to be expected to know about and be expected to kind of know what their graphs are going to look like. So keep working on the homework, and I hope to see you in office hours.